Welcome to part 2 of our regression review. This is lecture 6 of the course From Data to Decisions. And I'm Chris Mack, your instructor for this class. Last time we gave a broad overview of maximum likelihood estimators and under some assumptions showed that the ordinary least squares regression was a maximum likelihood estimator. We showed how we achieved this maximum likelihood by taking the derivative of the sum of the square errors, or the chi-square, with respect to each parameter that we're trying to optimize, setting them equal to 0, and then solving the resulting equations to find the values of those parameters that maximize the likelihood. Well, we did that with simple straight line fit as an example. What I'd like to do now is extend that concept to a model that has any number of predictor variables, any number of unknown parameters that must be fit. So we're going to do that by formulating the OLS problem in terms of matrices. Matrices are going to be either of dimension n or dimension p. So n is going to be the number of data points, and p is the number of parameters. We can number them 1, 2, 3 up to p, but because we like to use beta 0 for the intercept, beta 1 for the coefficient that multiplies x1, etc., you're going to have p minus 1 predictor variables who have p parameters. So we're going to set up our index, and I'll call it k, going from 0 to minus 1. Now, note that different textbooks and other sources might define p to be the number of predictor variables rather than the number of parameters. So be careful that people might use the letter p a little bit differently from text to text. But this is the notation that we'll use. As a result, our model will say y hat, the predicted value, is beta 0 plus beta 1 times x1 plus beta 2 times x2, etc. Each of these x represents a different predictor variable. Y sub I will be the ith response data value. So if I made measurements, I'll have n different data points. The ith data point, the output value is yi. And the input values are xi, comma k. So k represents the predictor variable, I represents data point number. All right. We will formulate all of our data in terms of matrices. So the output measured values, the yi's, will be a vector of length n, call it bold capital Y, and it's just listing all the data points from our measurements in order. The x values will be collected in a matrix that's p wide and n tall. We'll call that the design matrix. It has the values of all the input parameters, x's, in that matrix, and the first column will be all ones. Now, the reason we put the first column of all ones is this column is going to end up multiplying beta 0. Right? So beta 1 will be multiplied by x1, and beta 2 will be multiplied by x2, and beta 0 multiplied just by 1. So that's why we kind of put this artificial column of ones in the design matrix, because that's what's going to multiply by beta 0. And when we set up our matrices like this, and the model takes the form y equals x times beta plus epsilon, and epsilon are all of our residuals. Again, a vector of residuals that go from 1 to n. That, of course, is a very simple, compact form for expressing our model. We can see that it's a linear model in the sense that it's linear in beta, because y is directly proportional to beta. Also, you'll note that each row, x and y, represents a data point. So you run an experiment, you set all the x values to individual numbers, you run the experiment, you measure y. That's one data point. That's one row in one of these matrices. Every row is a different data points. I have n rows, n data points. Now, we're going to apply the concept of maximum likelihood estimation to this formulation, this matrix formulation of our problem. And to do that, we'll begin by defining the sum of square errors. Just like before, it's going to be the sum of all the residuals squared. We can represent the sum of the square of the residuals in the following matrix notation. It will be the transpose of the residuals multiplied by the residuals. Now, the transpose of a matrix is just a swapping of rows and columns. So take all the rows and turn them into columns. All the columns become rows. Because our residual is simply a vector, all one column, when I transpose it, I get one row. So I'm taking a row and multiplying it by a column, and that gives me the sum of the squares to the residuals. If I substitute in the definition of the residual, I get y minus x times beta transposed times y minus x times beta. We're now going to perform the same kind of maximum likelihood estimation that we've done before. I'll take this sum of square errors and take the derivative of that sum of square errors with respect to one of the parameters, beta sub k, and set it equal to 0. So we'll take this equation, take the derivative with respect to beta k, set it equal to 0, and I'll find that that's equal to the sum of the residuals times the kth predictor variable, all of its values xi, k. I do that for every single beta k, beta 0, beta 1, beta 2, beta 3, etc. One for every parameter. So I'll have p equations that are all of this form. Well, I can stack all those equations up in a matrix. When I do, what I get is x transpose times the residuals equals 0. And you can see kind of that format here for one particular row, which is one particular parameter. So now because I've done x transpose, every row is a different parameter. All right, well, let me take that equation, which is the equation we have to solve in order to find all the best fit parameters, the betas. I will take that and take the residual epsilon and substitute its definition, y minus x times beta. I do that, arrange a little bit, I get this equation, sometimes called the normal equation, which is the equation that we're going to try and solve. X transpose times x times beta equals x transpose times y. Again, everything looks nice and compact when written in this matrix formulation, which is value, one of the values of matrix formulations of these kinds of problems. All right, what do I have to do to solve for beta? I want to find the beta that causes, the values of betas that cause this equation to be true. I have to solve for beta. I will take x transpose times x, take its inverse. Multiplied by the inverse, a matrix times its inverse is equal to 1. So I will get beta is the inverse of x transpose times x multiplied by x transpose times y. This solution will be our beta hat. A beta hat will be simply our estimate of beta. And as I mentioned before, you'll sometimes use the hat notation for our estimate, and sometimes I'll use the Roman letter B as the notation to represent our estimate of the true value of beta. Well, that's it. As long as I know how to invert a matrix and do matrix multiplication, I'm done. Well, inverting a matrix can be a little bit tricky, but a lot of mathematical techniques for doing that. Most common is the singular value decomposition approach, and most software packages that perform matrix inversions in order to solve these equations and produce the OLS best fit parameters use something like a singular value decomposition approach. we're not going to worry about the numerics of it, the mathematics of it, other than understanding where these equations come from. Because we'll let a software package do these grunt work of doing the calculations for us. But once we've done this mathematical calculation, we've got our answer. We've got a vector that says here are beta 0 estimate, beta 1 estimate, beta 2 estimate, etc. We can also use that to calculate all of our best estimates of the parameter values, of the y values. Y hat. Y hat, our modeled value, will be x times beta hat. So I'll take x and multiply it by beta hat, which is directly right here. And I get this. Well, I notice that this is some great big thing multiplied by y. So I'll call that great big thing multiplying the y h. H has the name hat matrix. You might think, well, where do you get a name like that? I mean, the hat matrix? Well, if you take H, which we can, once we can invert this matrix, we can easily calculate this H matrix right here. Once we have hat matrix H, we multiply by y, and it puts the hat on y. It turns the actual measured data points, all the y values, into the modeled or predicted data points, y hat. Because H puts the hat on y, we call it the hat matrix. And the residual matrix, E, will be y minus y hat, which is simply the identity matrix I minus H, the hat matrix. All of that multiplied by y. Now the identity matrix is the equivalent of 1 in matrix form. 1, all the diagonal elements of the matrix are 1, and non-diagonal matrix elements are 0. Note that both the identity matrix and the hat matrix are square matrices, the same number of rows and columns, and they're also symmetric. Symmetric means that if you swap rows and columns, you get the same thing. It's the upper right-hand corner and the lower left-hand corner of the matrix are identical. We'll use that property of the hat matrix later on in the semester. And as I mentioned, there's common alternate notation of using b sub k instead of beta hat k. And I wish I could be consistent in my notation. I'll go back and forth. You'll find both of these notations commonly used in the literature and in textbooks and in papers that you read. So you should be familiar with both ways of notating our estimate for the true value of the parameters of the model. Well, we are now back to where we were in terms of solving the equation. We've got our estimates, but now we can do it not just a straight line model with a beta 0 and a beta 1, but we can have any number of predictor variables, any number of parameters that we have to solve for, and it all works the same way. It's the same matrix solution, just different sizes matrix. But we can also use this matrix formulation to calculate some other important things related to the covariance of the variables. Now, we've talked about covariance in the past. If you're unfamiliar or can't quite remember what the concept of covariance is all about, I recommend you go back to my lecture 15 of my statistics review course. That will explain a little bit about what the covariance is. But we can calculate the covariance of the residuals, the covariance of the predicted values, and the covariance of our estimated data parameters. So the covariance of the residuals is the variance of the residuals from our data set multiplied by I minus H. And for a given residual, E sub I, so the ith residual from my data, the variance of that ith residual is the variance of all the residuals times 1 minus, this is the diagonal of the hat matrix, H sub II. That's kind of interesting. If H sub II is 0, then all the variance will be variance of the residuals will be equal to a constant value. But if the HIIs are different, they're not all the same, they'll have a different variance for different residuals. This is a concept that we'll talk about later, called influence or leverage. Influence and leverage, two different related concepts. And we're going to talk about that in a couple weeks. We'll get to that topic. And we'll see that we'll need the hat matrix, and in particular its diagonal elements, to understand the variance of each of the residuals. Then we can also calculate the covariance of these residuals. Now, the covariance of the ith and the jth residual would be 0 if they were completely independent. But they're not. In general, they're not independent. You might be thinking, well, hold on a second. Didn't we say in the last lecture that one of the assumptions of our ordinary least squares regression was that every residual was independent of every other residual? That's true for the true residuals. True residuals are the epsilons of I. The covariance of epsilon I and epsilon j, two different residual values, will be 0, be completely independent of each other. But once we do a regression, because of the constraints on our regression, we end up adding covariance to the residuals, so that the estimate of our residuals for this particular data set will not be independent of each other. How much will they be dependent on each other? That depends on the off-diagonal elements of the hat matrix. Also like to mention that, note that every single one of these variances scales with the variance of the residuals. This is why minimum variance estimators, blue, the best linear unbiased estimator, is the one with the minimum variance of the residuals. This is why we care so much about the variance of the residuals. Everything about this fit will be better if the variance of the residuals is smaller. And we can see that here. So the covariance of y hat, my predicted y values, is scales as the variance of the residuals, and the variance of any particular predicted y value, y hat sub I, will also scale as the variance of the residuals, multiplied by this diagonal element of the hat matrix. The covariance, and this is maybe the most important part, the covariance of the estimates of each of the model parameters also is proportional to the variance of the residuals. We would like our uncertainty in our estimates of each of these parameters to be small. And that will only be true if the variance of the residuals is small. We're going to find that calculating the covariance matrix and using that to come up with our estimates of the uncertainty in each of the parameters and each prediction we might make with our model is an extremely important part of modeling. And we use these covariance matrices to perform those calculations. You'll see that they're always proportional to the variance of the residuals. If we have a simple straight line model, we've gone through this in the past. We have our ordinary least squares estimates for the slope and the intercept. But we need more than just the estimates of these parameters. We need estimates of their uncertainty. And that's where the covariance comes in. To determine the uncertainty of our fit parameters, we recognize that the population model, the true model, is estimated by estimating the values of beta 0 and beta 1 and estimating what the residuals are, E sub I. If we want to calculate confidence intervals about those, for example, what is 95% confidence interval of beta 0, B0? That is, if I ran the experiment 100 times, 95 times out of 100, value of B0 we get from our fit and within this interval. That's the confidence interval for that parameter. In order to generate a confidence interval, we need to know something about the sampling distribution. If we assume that our residuals are normally distributed, then the sampling distribution for each of these parameters is a t-distribution, an unbiased t-distribution with n-2 degrees of freedom. So if n is the number of data points in my data set, n-2 will be the number of degrees of freedom for the t-distribution of values of beta naught, beta 1, etc. All right. Well, for this simple case of a straight line model with only two parameters, a slope and an intercept, I can calculate with these equations the exact values of the variance of beta 1 and variance of B0, but I'll estimate them with the equations below. So first of all, our estimate for this variance of the residual will be the standard variance equation. Sum the squares of the errors here, and then divide by n minus p, where p is the number of model parameters. Right? So n minus p is the number of degrees of freedom. If we only have two model parameters, then it's n minus 2. You probably are used to calculating the standard deviation of a data set and dividing by n minus 1. That's because when you're calculating the standard deviation of a data set, you subtract off the mean, and that mean takes away 1 degree of freedom. So one parameter is the mean. So we do n minus 1. Here, when we calculate the standard deviation of residuals, or the variance of the residuals, if we don't take the square root, then we divide by n minus p, where p is the number of model parameters. So always remember that. You'll have lots of opportunities to calculate the variance and the standard deviation of the residuals. Make sure you always divide by n minus p instead of n or n minus 1, you might think to. All right, quick -2 on every one of your homework problems for exams if you get to do n minus p. Then, given that estimate of the variance of the residuals, I can calculate variance of the slope and the variance of the intercept with these formulas. Now, if I have more than just two parameters, if I have a model that's not just a straight line, well, I need to use my matrix formulation, and matrices can give us the variance and covariance of each of the parameters, as we've seen on the previous slides. Now we're going to use these estimates to calculate the confidence intervals about each parameter. So the confidence interval of the slope will be the value of the slope plus or minus a critical t-value multiplied by the standard error of the slope. The standard error slope comes from this equation. Take the square root of that equation and you have it. The critical t-value is the t-value you'd look up in a table of critical t-values or calculate it directly in a program like Excel. With n minus 2 degrees of freedom, remember n is the number of data points, and setting alpha at your significance level. You have to decide at what significant level you want that you think is important. A common value would be 0.05. If you want to do 95% confidence intervals, use alpha of 0.05. If you want to do 99% confidence intervals, you do alpha of 0.01. These are kind of typical values that many people will use. You have to decide what's right for your problem. So that will give you a critical value. Maybe it's 2.4, let's say. Multiply that number by the standard error of the parameter. Allow you to determine the confidence intervals. Here's the thing. Doing modeling work. You're fitting a model to your data. Maybe your model is a straight line. You want to report the best fit model. So you put into your report, into your paper, the value of the intercept and the value of the slope. You should always report confidence intervals. Telling me what the slope is without telling me what the confidence interval is about that slope is not telling me much at all. Is it very small confidence interval? Do I have a lot of confidence in the value of slope that you're reporting? Or is it a huge confidence interval and I don't really know much about the slope at all because the confidence interval is so large? To answer that question, you have to calculate these confidence intervals and you have to report them. We're going to do that every single time in this class. So you're going to have to get used to calculating confidence intervals for every parameter that you fit when doing modeling work. We can also determine the uncertainty of a prediction. If we're going to use my model to predict some behavior, I'm going to have an uncertainty in that prediction. And that uncertainty in the prediction will depend on the xi value. Am I predicting out at the extremes or somewhere in the middle? And if I put xi equal to mean value of all the x that I use to fit my data, I have a minimum level of uncertainty in my prediction. Notice that this part goes to 0. If I have an x value that's kind of at the extreme of the range of data that I've used, then I'll have a larger uncertainty in my predictions. Now this is the uncertainty in y hat. Y hat, remember, is the mean value. If I run an experiment over and over and over and over and over again, that's the mean value I'll get. And this is the uncertainty in my ability to predict that mean value. But if I run the experiment only once, and I get a new data point, y hat new, that has an uncertainty associated with just the standard deviation of the residuals, just the uncertainty in y itself, being added to the uncertainty of my prediction. So I have an uncertainty in the mean, and then I have a spread about that mean. And these two things add together to be the uncertainty or the variance of a predicted single data point. We're going to have occasion throughout the semester to make inferences about the correlation coefficient between two data points, or two variables, x and y. So the correlation coefficient is defined here. Again, you can go back to Lecture 15 to review what that correlation coefficient is and what it means. This is our estimator for that correlation coefficient for a given set of xy data. How do we make statements about the uncertainty of this estimate of the correlation coefficient for the given sample that we have? Well, if rho is 0, if the data is completely uncorrelated, then the value of R we get will be something probably a little different than 0, and it will have a student's t distribution, n minus 2 degrees of freedom, and a particular standard error given here. That's only for this special case when we have truly uncorrelated data. Well, that'll be a useful case, actually. We're going to make use of this particular case a few times. But there are other cases where that's not true, and this is a little bit more rare, but if we want to make inferences about a correlation coefficient that's not equal to 0, we have a very complicated sampling distribution. To fix that, we use the Fisher Z transformation and essentially take my sample calculated value of R and convert it to a Z. Then if the number of data points is reasonably large, bigger than about 25, then we'll see that Z is normally distributed, the particular mean and variance as given here. And given that, we can come up with make our inferences about the measured correlation coefficient. All right, that just kind of fills out our description of uncertainty of the parameters in our fit, making use of matrix formulation to perform the calculations of the covariance. So, what have we learned? You should be able to quickly and easily answer these questions. Why is the matrix formulation of ordinary least squares commonly used? What are the advantages of the matrix formulation? What is the hat matrix? Why is it important? We kind of haven't really talked much about it. I hinted at it. We're going to use the hat matrix later, but you should have an idea of why it's important now. And the main thing here is you should be able to use the results of this lecture, those equations, if we do a straight line fizz, or the results of an algorithm or a software package that does the matrix calculations, use the standard errors to calculate confidence intervals for all of the model parameters coming out of your fit and for predicted model values. It's going to be a big part of what we do in this class. Not only will we do best fits of models to data sets, but we'll describe using confidence intervals our uncertainty of those best fit estimates. That's the second part of our review lecture on regression. We'll have the last part next time. Till then.